Now that we learned all about the octet rule, we have to tell you there are exceptions to the octet rule. Perhaps the most obvious one are molecules or ions which have an odd number of electrons. How can you share and have everybody end up with 2 or 8 if you have an odd number? Well, it's just not possible. You've probably heard of free radicals. The health community is real big on, we need to do things to reduce free radicals, and free radicals are bad. And yeah, they're not good in your body. Free radicals are molecules and ions that have an odd number of electrons. So it's not possible for all the atoms to have an octet. These tend to be unstable and very reactive, and that's why they're not good in your body, because they're going to react in ways that your body maybe doesn't want them to react. So let's draw the Lewis structure for no nitrogen monoxide. Well, this is going to be relatively simple. It's going to be nitrogen and oxygen, right? There's 2 atoms. You can only connect them one way. It's a relief after that last one. How many electrons do we have? Well, nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. That gives us 11. Good luck on this, right? So 2, 4, 6, 8, 10, 11. Okay, in this picture, nobody's happy. We got to make at least one person happy, one atom happy. So let's make a double bond and see if that helps. We'll take that lone pair and we'll make a double bond. And now how do we stand? This nitrogen has 2, 4, 6, 8, and the oxygen has 7. Right? Well, there's another possibility. We can't move the double bond, but what if we give oxygen the octet and nitrogen that lone electron, and he's an electron short? Well, how do we choose between those? We can't draw a structure, a Lewis structure, that fulfills the octet rule. It's just not possible. And this is one of the limitations of the Lewis model. It can't deal with everything. Nitrogen monoxide does exist. It's in air pollution. It's reactive, and it's not a good thing to have in your air, but it exists. So what do? Well, we just make the best of a bad situation. We just draw the best Lewis structure we can. So how do we figure out which one gets the odd electron and gets short? Formal charges. Oh, here we are, formal charges again. So this nitrogen here, in this Lewis structure, he owns 6 electrons. 4 from the double bonds and half of each bond. Owns 6, came in with 5, so he has a formal charge of -1. The oxygen has 6 valence electrons, and here has 1, 2, 3, 4, 5. So +1 charge. Let's look at the other one. What's the formal charge on nitrogen here? 0. And on the oxygen? 0. So drawing the Lewis structure, we'll do this one, because the formal charges are 0. So we're just going to put that odd electron where we can to minimize the formal charges and say, there we go, that's the best we can do. Any questions? There are not a lot of free radicals that we'll run into in this class, but they do exist, and we have to recognize that. Another way you can violate the octet rule is by having an incomplete octet. Now here, the odd electron was incomplete as well, but here we have pairs. We have an even number of electrons, but we have an incomplete octet, meaning less than 8. And some elements just tend to do this, and boron is one of them. So we're going to draw the Lewis structure for BF3, boron trifluoride. I think we can do it down here in the bottom. So boron and 3 fluorines. What's probably the best way to put that skeleton together?
Be in the middle.
Boron in the middle and put the fluorines around. Because when we look on the periodic table, boron is several squares over from fluorine, and we know that fluorine is the most electronegative, and generally most electronegative element goes on the outside. So we're going to go with that. And then how many valence electrons? Well, we have 3 fluorines. They each have 7. And we have boron with 3. 3 times 7 is 21, plus 3 is 24. So we got 2, 4, 6 for the bonds. 8, 10, 12, 14, 16, 18, 20, 22, 24. So what would we usually do in this situation? We don't have enough electrons for everybody to have an octet. We would have a double bond, right? So I'm going to leave that guy alone, and I'm just going to draw one over here where we would do a double bond with one of the fluorines. And then you can think, oh my goodness, then there's all those resonance structures. Yeah, we're not going to think about that right now. That one looks better, doesn't it? Everybody has an octet. The boron, all the fluorines, they all have octets. What about the formal charges? What is the formal charge on this fluorine? 0. Fluorine has 7 valence electrons, and in this Lewis structure, it has 7. And so this one is also 0, and this one is also 0, formal charge. What's the formal charge on the boron? 0. It's violating the octet rule, but the formal charges are looking really good. What if we put a double bond? Well, these guys are still going to be 0. This fluorine now, what's its formal charge? +1. Is that good for the most electronegative element? No. What's the formal charge on the boron? -1. The formal charges help us to see this is the true structure of boron trifluoride. Now, how do you know to do that? Well, boron tends to form compounds that violate the octet rule. And if you look at the periodic table, boron is one of the smaller elements, isn't it? And it's the smaller children in the family that violate the rules sometimes. We don't give that one as big a plate of spaghetti because she can't eat all of it, right? So if that helps you to remember, the smaller ones are more likely to violate the octet rule. Hydrogen and helium are so small that they don't even aspire to hit the octet rule. They've got their own rule, the duet rule. So boron's down there doing this thing, and beryllium also tends to have incomplete octets. Now, when this reacts with something, it will react in a way that may complete the octet on boron. And so it's not that boron never obeys the octet rule, but it's not uncommon for it to disobey. It's kind of a naughty child. We don't talk about lithium not obeying the octet rule because lithium is an alkali metal and it just forms ionic compounds. Beryllium's getting a little iffy there. Sometimes he forms covalent compounds. Anyway, incomplete octets. It's a possibility. So, too few electrons, we can also have expanded octets, more than 8. This happens with the larger elements. So elements in period 3 and above is where we can see this happening. And the reason is that these have d orbitals that they can expand into. And we'll see more about that later. But if you have elements in period 3, these are things like phosphorus and sulfur or bromine or things like that. It's possible for them to do expanded octets, sometimes up to 12 or 14 electrons instead of 8. So it can be significant. So we're supposed to draw the Lewis structure for arsenic pentafluoride and sulfur hexafluoride. And there's like 0 room there, but that's okay, we'll do it anyway. Because last year I didn't have doceri, and so I just was writing on the wall, and space wasn't an issue. So what these guys are going to do, the arsenic is going to be in the middle, and the fluorines are all going to be bonded to it. This violates rules that we have learned. I'm sorry. That's the Lewis structure for that guy. Arsenic here has 10 electrons instead of 8. The reason is that arsenic is actually in the 4th period. He has 3d orbitals and 4d, it would be the 4d orbitals. He has 4d orbitals that he can bump electrons up into and accept those extra electrons. And sulfur hexafluoride, it's going to be sulfur, and it's going to have 6 fluorines around it. I'm going to have to make my electrons smaller. If we look at that sulfur hexafluoride, if you want to count up all the dots, it's the right number. I encourage you to check me on that, but I don't want to do it. What's the formal charge on the sulfur? 0. And what's the formal charge on each of the fluorines? 0. It's a good thing. On these fluorines are also going to be 0. What's the formal charge on the arsenic? 0. Arsenic has 5 valence electrons. In this structure, it has 5 electrons. Its formal charge is 0. So if you find this a little disturbing, that's okay. It should be a little disturbing. It's weird. It happens. I'm sorry. We ignore this for the most part in Chem 3A. But Chem 1A, we got to tell you a little more truth. Sometimes the truth is not what you want to hear, but yeah, you're older now and you need to know. You want to look on at the formal charges on sulfuric acid? Like, no, we don't. Oh, well, let's do it anyway. Let's just finish this slide and then I'll make a clean one. What happens is that the expanded octets tend to lower the formal charge for period 3 elements, and that's what we're going to see when we do this. The period 2 elements never have expanded octets. They just can't do it. So boron, carbon, nitrogen, oxygen, fluorine, they cannot do it. The only reason the larger ones can is they have d orbitals that are available. Because look at sulfur. Where are the the Lewis. Where are the valence electrons for sulfur in the electron configuration? It's got 6 valence electrons. They're going to be 3s2, 3p4, right? So what happens when it shares is that those orbitals are involved. It's going to essentially fill up its p to 6. And then how can it take more electrons? It can also borrow from the d orbitals. We'll see more about that when we get into molecular orbital theory. So let's look at sulfuric acid. So H2SO4. So the sulfur, and then there's, let's try putting 4 oxygens around it. And then we'll just hang the hydrogens off of a couple of the oxygens and call it good. Number of electrons, sulfur has 6. There's 4 oxygens, they each have 6. And there's 2 hydrogens, they each have 1. So 5 times 6 is 30, 32, right? So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 32. Did I do that right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I did not. 32. Did I do it right this time? You guys awake? Still here? You're being very quiet. So that looks great, doesn't it? Like, wow, that worked out really well. What do you want to mess with that for? Well, let's look at the formal charges on this. We don't have to worry about the hydrogens. This oxygen, what's the formal charge? 0. This oxygen. -1. This oxygen. 0. This oxygen. The sulfur. +2. Satisfies the octet rule really nicely. The formal charges are a little sketchy. Well, what else could we do with this guy? Sulfur is in group 3 in the periodic table. We could try an expanded octet. So we didn't do this before, but now we're going to try something. Okay, so let's look at this guy, and here, this oxygen really has too many electrons, right? So let's get some electrons off of him by making a double bond with the sulfur. I'm going to straighten this up a little bit. Those guys are up there. And then I'm going to say, so let's put the electrons in first, and then move them around. I think that'll be more clear. So this is what we had above. And I'm going to move electrons around, and I'm going to try to get a better outcome for my formal charges. And let's be just clear, those guys got awfully close together. So this oxygen had a negative formal charge. That means it's got too many electrons. So I'm going to take one of its pair of electrons, and I'm going to make it be a double bond. When I do that, the oxygen still has an octet, And now I've given sulfur more than 8 electrons, which we said we shouldn't do previously. But we're talking about expanded octets here, and sulfur can do that. What is the formal charge on this oxygen now? It's 0, right? And what is the formal charge on the sulfur currently? +1. So that worked, didn't it? The other one that had a problem, besides the sulfur, was down here. So let's do the same thing and take that lone pair off and make it into a bond. And now this one also has a formal charge of 0. And the sulfur has a formal charge of 0. And these guys still have formal charges of 0. That's better. Sulfur can do it because it's a group 3. If you had nitrogen in there, it's not going to work because nitrogen can't. Group 2 elements can't, period 2 elements can't do it. Questions? Period 3 and above. Period 4, 5, 6, 7, 3 and above. 1 and 2, absolutely not. Arsenic is in group 4. Period 4. Periods 3, 4, 5, 6 can do it. Period 2 cannot. So arsenic being in period 4 is fine with an expanded octet. So write the Lewis structure for xenon hexafluoride. Not hexafluoride. Tetrafluoride. What's weird about this compound? It's got noble gas in it. They don't form many compounds, but they do form compounds. Okay, so we're going to put xenon in the middle, and we're going to put the fluorines around it. This is usually how things go. And how many electrons? We've got 4 fluorines. They each have 7 valence electrons, and the xenon has 8. So that's 28 and 8, that's 36. Is that right? So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Where are we going to put those electrons? On the xenon. 34, 36. That gives xenon an expanded octet. Is that possible for xenon? What group is he? What period is he in? Period 5. He can handle it. He's big enough to handle an expanded octet. What are the formal charges? They're 0 on everything. Very reassuring when all your formal charges come out to be 0. I'm going to tell you a little, it's kind of a trick. And so let's look at, here we've got fluorine. Fluorine has 7 valence electrons, right? So when we do it like that, it has 1 unpaired electron. Fluorine tends to form 1 bond. Oxygen, 6 valence electrons. 1, 2, 3, 4, 5, 6. How many unpaired electrons? Oxygen tends to form 2 bonds. Nitrogen, 2, 4, 5. How many unpaired electrons? Tends to form 3 bonds. Carbon. Oops. If you go back and look at the Lewis structures we've been doing, you'll see that this happens most of the time.
The font rule.
Pardon me?
FONC, the font rule.
Yeah, I guess so. It's easier to say than the other way, CNOF. But this is true of the other elements in those groups as well. Sulfur has 6 valence electrons. It has 2 unpaired valence electrons. It tends to form 2 bonds. Now, we just saw in the previous slide that sometimes it forms more. And it can do that by expanding its octet. But these are kind of general trends, and recognizing this can help you when you're trying to put those skeletal structures together. A good place to start is having nitrogen have 3 bonds. Okay? A lot of times nitrogen does a triple bond or a double bond with somebody and a single with something else, but it'll end up with 3 bonds. So that's just kind of a background thing to keep in the back of your head. And if we look at this thing that we drew here, each of these fluorines has 1 bond. Because it just needs to get 1 more electron. And so by making 1 bond, it gets that electron, it gets its octet. And usually they say, good enough, stop. And then there's the bigger guys, they get a little greedy sometimes, like the xenon. Xenon had 8. Why is it going to do this? Well, it doesn't do it very much, but there it did. It did it. H3PO4. If that is dissolved in water, what's the name of that? Phosphoric acid. Because if we cover up the H's, that's phosphate. 8 and ic go together, so that becomes phosphoric acid. Phosphoric acid. Okay. Lewis structure for this. See, this is where we're paying for putting off yesterday the rest of the lecture. Well. So we're going to put the phosphorus in the middle and try putting the oxygens around it, and then put the hydrogens. A good place to start is something really nice and symmetrical like that. It says, if necessary, expand the octet on any appropriate atoms to lower formal charge. So we're just going to go ahead with our straightforward drawing Lewis structures. Phosphorus has, question? I'm missing an H, thank you. I am. I don't know what I was thinking. There we go, that's better. That's why I need you guys here. So we've got 3 hydrogens, and they each have 1 electron, valence electron. And the phosphorus has 5, and there are 4 oxygens, and they each have 6. So we've got 24, and 5 is 29, and 3 is 32. It's fine to use a calculator to add those up. I just don't want to dig mine out and walk 2 steps over there. Okay, so what do we have here? We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That looks pretty good, right? Got the right number of electrons. Everybody's got an octet. In 3A, you close the book and go home. Good. But we know about formal charges. Let's check the formal charges. Is phosphorus large enough that it could do an expanded octet? What period is it in? It's in period 3. Phosphorus sometimes does an expanded octet, so we need to look at it and see what's going on here. So, again, we don't need to mess with formal charges for the hydrogens. What's the formal charge on this phosphorus? +1. Oh, we'd like it to be 0. How about this oxygen? That one's 0. Good. And then these guys, they have the same number of valence electrons, same number of lone pairs and bonds are also going to be 0. What about this oxygen? -1. Oh. We can lower the formal charges by expanding the octet on the phosphorus. This oxygen has too many electrons, and the phosphorus doesn't have enough. So I'm going to take this lone pair and give it to a double bond in here. By doing that, I have the same number of electrons in my structure, and the oxygen still has an octet, but now phosphorus has an expanded octet. And let's check the formal charges. Well, what's the formal charge on this oxygen now? 0. And on the phosphorus? 0. Is that better? Yes. So that's the best Lewis structure for phosphoric acid. Questions?